Good morning. Last lecture we discussed the basic properties of a p-n-junction diode. We designed the device by using a n-type and p-type material that are doped appropriately that had interesting properties. Specifically, what they did, it had an exponential IV characteristic, namely the current was exponentially related to the voltage, and as such, it was kind of a rectifier, right? I mean, it was what we call a diode. Diode is a general term. Now, in fact, actually, the name diode comes from vacuum tube days, because you have the diode, then you had the triode, then they had the tetrode, and the pentode, and all those things, depending on how many electrodes you had. So diode was the simplest one, which had 2 electrodes. So diode in general now refers to any device that basically has this rectifying nonlinear characteristic that is more conductive in one direction and less conductive in the other direction. So it's like a one-way valve, if you will. An ideal diode, of course, is like an L-shaped IV characteristic. Now, p-n-junction is one way of making a diode. Now, most of the diodes today are made out of p-n-junctions, so we basically just has become synonymous. But diode is more general. P-n-junction is a special kind of a diode. Anyway, so what we did, we could make a diode, basically meaning that we had a P and N, and what we saw is that we had 2 regions. So let's go through that process very quickly. So if you had a Pn, so let's say you had a region P, let's say a region N and a region P. And what do we have? What kind of dopants did we have in the N region? To get N region basically means that you have more electrons than holes. So you have things that are easily giving away extra electrons. So you need column 5 elements, right? Which basically, after they give up the electron, they leave behind a positive ion, right? So you had these positive ions. And the free electrons, right? You had the free electrons at room temperature. Most of them were ionized, so these electrons were really free. They were not attached to any of them, so they were moving around free. And on the P side, what we had a bunch of acceptors, basically column 3 elements, which would be able to easily ionize at room temperature. And what that does is basically, when they ionize, they leave behind a free hole. So you had the hole at room temperatures, you had the holes that were free to move around. Of course, these ions cannot move around. These are massive relative to the holes and electrons. They're atoms with nuclei and bunch of other electrons that have formed bonds, 4 covalent bonds with the adjacent silicon atoms. So these are pretty well tied down. But the holes and the electrons that they release, they are pretty free. And of course, these things the other thing that we calculated was the speed by which they are randomly moving thermally. We saw that the speed of random thermal movement was extremely high. And these being small devices, it's very quickly, the chance of these guys ending on the other side is pretty high, because they're moving around, and every so often they will move on end up on the other side. When there's now, for example, an electron moving from this side, ending on the other side, is a minority carrier, because now there's a lot of holes around it, and it has a high chance of recombination. Now, the closer you are to the junction, the higher this chance is, and it's really an exponential drop beyond a certain point. But at that point, there is a region. You basically eventually form a region which is depleted of charge carriers. So most of the charge carriers in this region have already recombined. Of course, you're constantly generating new ones, electron-hole pairs, that as they are generated, due to the electric field that's generated in this direction, which basically pointing which way? The electric field, if you put a positive charge here, it's going to go this way, right? So the electric field is pointed this way. So this electric field would force them to, so if you have an electron and hole generated, the electron would go this way, where it's majority, and the hole would go this way. And there's a component of, this is basically balancing the net flow, because there's always some hot electrons and hot holes that would just cross the boundary, that would be able to cross this barrier. And if you look at the energy band diagram of something like this, what you have is that you have an n-type on this side, right? So your Fermi level is closer to your conduction band. Then you have a p-type on the other side. And in thermal equilibrium, you had a Fermi energy, EF, that's constant across. And here you basically are, you have more holes and you have more electrons here. So this was the energy band diagrams. And of course, an electron needs to work going, basically what you see is that if I put an electron here, it would go down this way, the electric field would go this way. And if I put a hole down here, the hole would go down this way, because these are the energy levels upside down, because these are the energy levels for electrons, right? So this was the basic picture we showed last time, right? This was the general picture. And of course, again, I want to emphasize the difference between thermal equilibrium and steady state. Now, if you leave it like that, if you don't connect it to anything else, it's in thermal equilibrium. Now, one of the things we did was, of course, to make this diode forward biased, right? When you apply a forward bias, there will be current flowing, right? We saw that there will be current flowing is exponentially dependent on this V diode. And the way it happens is that you're basically lowering this potential barrier. So what happens is that when you apply a voltage like that, you're lowering this potential barrier by VD, by QVD really, and you're lowering it here the same amount. So now you had a really Fermi-Dirac distribution, but it's really approximated as Boltzmann distribution of electrons. So you have electrons on this side. So before, only these electrons were hot enough to cross. Now by lowering the potential barrier, you have a whole bunch of new ones that can cross. And these guys are still bounced back. And the same thing is true for the holes. You've lowered the potential barrier for the holes. So now a whole bunch of new ones that couldn't pass can pass now. Right? So this was a picture that we had. And now this current may be a DC current, maybe a constant DC current. But it does not make the system in thermal equilibrium anymore. So basically you will not have a constant Fermi level across this thing. It's meaningless to define that, because Fermi-Dirac distribution is meaningful only in thermal equilibrium. Now you are in steady state, but you're not thermal equilibrium. And what sometimes people do, they define as quasi-Fermi levels. That there's a local Fermi level here and there's a local Fermi level there, and they're different. And the difference is, of course, QVD. So that's the picture that we developed last time. Now, this is a kind of a useful device, of course, as a diode, but it's not particularly useful. I mean, if you just had diodes, making logic circuits and amplifiers and analog circuits and digital circuits would be very difficult and practical, and in many cases impossible, right? How do you make an amplifier? What do you need to make an amplifier or a logic switch if you want to make a logical gate or an amplifier? You need, what is the quality, what is the property that you need for that device to be useful? What property would you like the device to have for it to be useful? Any thoughts? What is missing from this?
You can't control it with some other input.
Right, exactly. So the response was you cannot control it with some other input, which basically means that you really need a third terminal. You need to separate the controlling terminal from the controlled. Because here the controlling and the controlled are one. You have these two terminals which basically make one port. You need to have at least one more terminal to control what's going on. So this process of making a bipolar junction transistor from a pn-junction diode is really based on that. I mean, it's essentially, fundamentally, it's as simple as that. So let's see what we can do. What is the controlling parameter here in this device? What is the thing that controls what happens to it? What is the variable, a seemingly independent variable, at least in this case? What is it? It's the voltage, right? It's this voltage that you're applying here, right? And what does this voltage do? It lowers adjusts the potential barrier. So, and what it really does, it actually is really harnessing the thermal energy. All it's doing is just lowering the potential barrier, and the thermal energy does the rest of the work. Just the electrons will pour in, and the holes will pour in this direction. All you do is just need to adjust that knob. So it's a useful knob because you control the voltage, and then the thermal energy is doing a lot of work for you. And that's why the bipolar junction transistor has so much transconductance. When we compare it, for example, with MOSFET, is that you are really harnessing the thermal energy. And that's what makes it such a powerful device. It's a very, I mean, if you use some sort of analogy, it's a very bulky, beefy, buff device, right? I mean, in that sense. Okay, so what is happening? Before we kind of like, okay, the obvious step is, of course, to add a third terminal, right? And of course, the obvious step is that, you know, you have an N, you have a P, so you want to put another N here or another P there. So this is kind of obvious, but let's think about it, about why we do it and how we do it. So let's be a little bit more purposeful about it. So let's redraw this picture, but in a slightly different fashion. So I'm not going to redraw all the ions again, but what we are going to be looking, so this is the junction, let's say, and then you have the N-type and P-type. And let's look at the current distribution when you have a forward bias applied to it, which in this case was like that. So you have a forward bias applied, you have a depletion region, right? So let's say this is the depletion region. And I've drawn in this case the depletion region, I don't know. I mean, well, let's draw it. Which side would the depletion region extend more into from what we learned last time when we calculated the capacitance and the depletion region width? Which side has the larger depletion region? The lighter doped side, right? The side with the lighter level of doping concentration. You saw that the depletion region extends more in that sense. So in this case, the way I've drawn it, it means that the p-type is slightly less doped. The concentration of the acceptors here is slightly lower than the concentration of the donors here. Okay, we'll see that this is important when we design our device. We'll talk about it. Not this exact arrangement, but this knowledge and understanding of the depletion region width. Okay, so, and then how about the currents? So what is the current? So there's some current I that for a given cross-section A corresponds to some current density J, right? So there's a J total going through the diode. Now, this current, this total current has to be constant, right? This total current, this J total, if the cross-section of the diode doesn't change, the total current has to be constant, right? Otherwise, you're violating conservation, at least in steady state. Otherwise, you're violating conservation of charge. So, but now the question is, what is the breakdown of the electronic current and the hole current? The current carried by the electrons and the carried by the holes. And that's very important to understand in the development of subsequent devices. So let's think about it. So where is the let's start with the P side. Where is the electronic current coming from? Why do you have electrons here? Where are these, if you have electrons carrying current on this side, where are they coming from?
From the inside?
Exactly. They're coming from the N side, right? They are these carriers that are majorities, but they were injected into this thing, so they became minorities on this side. So they are minority carriers. And as they go, so at the edge of the depletion region, you have a certain concentration. You have a Jn here, right? Let's say, I don't know, some level, just a Jn. Or maybe a little bit more upright, Jn. So what would happen to them once they're in the P side? They're minority carriers. There's a lot of chances for recombination for them because there are lots of holes there around them. So the chance of one of them running into a hole is pretty high. Now, the farther they go in there, what would happen to this chance? The more you go, the more chances you will get, right? So as you transition, you expect the number of these electrons that are injected in this region to drop. And you can actually show it pretty easily. That's an exponential drop. And how do you know it's an exponential? Because the chance of recombination is proportional to the number of the electrons to begin with. If you have a process where the rate is proportional to the number, you get an exponential because you get a first order differential equation. Any process, it's called a relaxation process sometimes. Any process where the rate of something is proportional to its current value gives you an exponential. Radioactive decay is like that. You know, the RC time constants are like that. A lot of things are like that. Okay, so these guys will exponentially drop. And of course, once they get to this junction, they will have to recombine anyway, because now you have a 3D. What we haven't shown is that there's some sort of another contact here and there that will have its own little potential barriers and all. But let's not worry about that. So let's say these are relatively long for now. Now, of course, now how about the holes on this side? If you think about the holes, well, I think I messed up my color code. So, now, how about the holes on the other side? The holes, similarly, the same story for the holes. So the holes are kind of like also decaying. So JP looks like that. Now, what can you say about the total net electron current on this side? So where is the rest of the current coming from? This J total has to be constant. So whatever is not carried by JP has to be carried by Jn. You say, why is there a Jn? Well, the electrons still have to be injected into this thing and going through to make up for the electrons that are lost to these recombinations and make up for the electrons that are injected. Right? There are electrons that are going to the other side, and there are electrons that are lost in this recombination. So you have to replenish this missing electron. So it should not be surprising to you that this would be complementary to the shape of what you already have here. So this is going to be the Jn. Well, it has to be matching this, of course, here. Something like that. So I'm assuming this picture assumes that there's no major loss in the depletion region of these carriers, right? So whatever makes it to this edge is going to make it to the other edge. And then same, in a similar fashion, you have this happening here. So that's the JPJ. So this picture is important because this allows us to think about what we need to do to control and play and manipulate these charge carriers. Now, what is the thing that dictates the shape of this plot, the JP on this side, and the shape of this plot, Jn on this side? The shape, the distribution of the current by the majority carriers.
The dopant concentration?
Is it the dopant concentration that dictates this? Because I basically assume that constant doping concentration here, right? I mean, yes, the doping concentration will have some second order effect. You're right about that. But there's something that's first order before that happens. What is dictating this shape? Why this blue line is like that? We argued why the red one is like that, right? We argued why this one is an exponential. We said this is like a recombination process. You lose more. The minority carrier distribution is this way. How about the majority carrier distribution, which is these two? Why does it have the shape it does? What dictates that shape? Could it have any other shape when this one was already had this shape? No, because the sum has to be equal to the J total. So interestingly, the distribution and behavior of the majority is dictated to some extent by the behavior of the minority. Which is interesting to think about, right? So it is really the minority carriers that dictate the behavior of the majority because they're responding to them. This one and that one. And this is the basis of how you basically design a bipolar transistor, or in general, a lot of devices. It is the minority charge carriers that dictate the behavior here. So now, if you wait till here, so how can I harness this thing? Because if I let the minority carriers to basically just like go and propagate, eventually most of them and eventually all of them will recombine. So you have lost that leverage really over them. You want them to be used in a different location. So you want to absorb them to a place where you can manipulate them without significant amount of recombination. So you want to get them into a region where there are majority carriers again. Right? Does it make sense? So how do we do that? We have to create a region where these ends are, for example, majority carriers, right? What kind of region would do that? An n-type. And that's why introducing another n-type here would basically be the basis of what makes a bipolar transistor. So it's a bipolar junction transistor, or BJT for short. So in a BJT, you have, let's say this is an NPN, and you can have a PNP. So let's say we'll talk about an NPN. So you have the N and the P, right? So that's the diode we had already. But now we want to absorb these minority charge carriers somewhere before they are completely lost in recombination. And that's why you introduce another region, N, here, where they can be absorbed before they're completely recombined. So, and how do you, of course, this one is your controlling voltage, right? So now this is a voltage, which will have a name soon, applied here. Let's call it V1 for now. Now, here, what are you doing? So what happens is that by lowering the potential barrier here, so if you look at the energy band diagram, let's have the energy band diagram on this side. For this first junction, you're forward biasing it. So you have lowered the energy band diagram, the potential barrier. You've lowered it from where it would have been to here. So it would have been like that. And by applying this V1, you've lowered that potential barrier. So now, as a result, a bunch of your electrons that could not pass before, so these are the ones that could pass before they were hot enough to pass that potential barrier. Now you have a much lower potential barrier, so lower potential barrier, so these guys can pass, and these guys are bounced. So here's the thing. You've applied this, and they are injected into this region. So you're emitting electrons from here into this region, and then you want to collect them here. Right? You're emitting your charge carriers from here, and you want to collect them. Now, if you want to facilitate the collection, what kind of electric field would facilitate, if I said, okay, well, I want to make an electric field that would facilitate this collection process, which way should that electric field be pointing to facilitate collection of electrons into here? So you want electrons to go this way, which means that you want the electric field to be pointing this way, right? So you want an electric field here. We know the electric field in this region, in this part of the depletion region, is pointing this way. But now you want an electric field that's pointing this way. And to produce that, of course, this kind of p-n junction does produce that naturally, because you have negatively charged ions here and positively charged ions there in that picture. So if you have a depletion region here, what you have is that you have negatively charged ions and positively charged ions here. I'm not going to draw all of them. I'm just going to draw a representative. So that's basically what generates the field. So what you need to do, and if you want to increase this field, what kind of bias should I apply to this p-n junction? Reverse or forward? Reverse, right? So the reverse would look like this. And this should really be connected this way. So this is the essence. So what happens is that by applying a reverse potential bias, reverse electric potential, I am actually making this a steeper thing. So the electrons, once they make it past this barrier, it's kind of going to be downhill for them. So because they are going to go here, and they're going to be absorbed in the collector. Now, what makes them go from here to there? What makes them traverse? There are several different things, but there's the first order thing. By far first order, but stronger than the other effects, the other major two second order effects. What is that number one effect that makes the electron get from here to there? What is it? What do you think it is? Thermal energy, right? Exactly. Because remember, they are still pretty darn hot, and they're moving pretty darn fast. So what's happening is that once they're in the base, they're not making a lot of, for the most part, there's nothing special happening. They're just moving randomly around so fast, and every so often, one of them ends up in this region and gets sucked in. Goes downhill. And this is important to understanding some of the behavior of the device later on when we talk about it. So, okay, fine. So this is happening, and that's good. Now, a few questions about this device. Now, the most basic question. So we are designing a device. We have some thought about this process. So this region, by the way, is called what? Obviously based on what the argument that we had. This is called the emitter, where the charge carriers are emitted from. And this is where they're collected, so it's called the collector. And this is called the base for a historical reason. And historical reason is this. if you look at the first transistor, well, the first demonstrated transistor, which was by people at Bell Labs. The transistor was invented 20 years before that by Julius Lilienfeld. He has 3 issued US patents that you can go and read, and they describe the transistor. So this is one of my things. But anyway, so if you look at that transistor, which actually is interesting, I have a picture of that I took myself when I was at Bell Labs. But anyway, so interesting thing is that the way it was a point contact transistor. It was not a BJT. It was not this kind of transistor. One of the things that the way they made it is the following. So they made a little wedge of some non-conductive material. And then they had a coating of conductive material on it. And they were trying to make these 2 points pretty close to each other. So they made a little cut there. And then they mounted on a substrate, on its semiconductor substrate. So this, if you will, would be one of them would be the collector, one of them would be the emitter when it's mounted on this. So maybe it's easier for me to mount this on top of that, the way I've drawn it. Okay? So there were 2 regions formed, 2 kind of semiconductor regions. So they had a tiny base, tiny emitter, tiny collector, and a gigantic base, which was that middle terminal. And that's why it's called base. Now this makes sense why it's called base. But anyway, so that's what it's called. So this is called the emitter, the base, and the collector. These are the names. So we will be referring to them as such. Now, and obviously these voltages, we call them appropriately. So this is VBE, the base emitter voltage, and this is VCB, right? The voltage between collector and the base. So, okay, fine. So this is the basics and thing. But now the question I have for you is that if you want this to behave the way we think about, meaning that you want a certain distribution of the charge, most of the charge carriers, the minority charge carriers, to be absorbed into the collector, what do we need to do about this base? What are the things that we have to do? Yes, Nikhil. Make sure it's thin enough, right? You don't want it to take too long for them to go through this region. So you want to make it as thin as possible so that you can make it across as quickly as possible. So you want to make it thin. And so that's the first order thing. You want to make this base as thin as you can possibly can. Of course, there are some other considerations that will come in when you do that. But the thinner it is, the more they would go through. Now, the other question I have for you, and this is part of one of the homework problems that you have to do, is what do you think the distribution of the minority charge carriers will look like if this base is thin? How would this charge look like? Let's say in this case, the minority carriers would be electrons. If it was a PMP, it would be holes. But what would they look like? What do you think the distribution looks like in the base? You have a suggestion? Any thoughts? Straight line. Okay, so that's how. So it looks like a straight, like that. You didn't mean flat line. Okay, so you meant a straight inclined line. Okay. Which one do you like? This one or this one? Flat. So how many people like this flat? How many people like the inclined line? Okay, so we have one group of each. So let me ask you this question. What determines this? We are not talking just about, so remember, these electrons are going through this region. It's just a possibility of finding this electron. And this is basically what the homework problem will show you, and you will see it in the homework problem. So now assume that each one of these electrons are moving randomly, right, thermally. If you have random thermal movement, the probability of finding an electron here at this edge is higher, or is it higher to find it here, where they were just injected? So the closer you get to this region, the more likely they are that to have that pass through. And this is something that you will show through a simulation. And you will not only show that, you will not only see that the distribution is like this, because there's a higher concentration of them. You see, this is basically a variation on this exponential. Think about this exponential, right? But imagine that this was very short. Now, if this was very short, this would drop very rapidly, because eventually they have to get recombined once they get to the other edge, or they have to be absorbed. And in this case, they are not recombined; they're absorbed into the collector. But what happens is that in your homework problem, what you're doing is that you're taking some number of particles, you're assuming that they have an equal probability of 1/2 to go this way and 1/2 to go that way, and then you just pour them in there, and then there's a source here, so there's always a density of them here, and then there's always absorbed here, and you will see what they look like after a while. You let it evolve, and you will see what happens. And you will see that it forms a distribution. So this is basically sometimes called Q base. This is the minority charge carrier in the base. Sometimes we refer to the total charge as QF later on, but we'll talk about that. But this distribution, this is what controls the behavior of the device. Now, the narrower you make this, the more of them make it to the other side. And few of them get recombined, because there's always a chance of recombination in the base. So that's the number one thing that you want to do if you make this transistor, is to basically making sure that this concentration is, this width is small. So what is the current? What is the collector current? So if I look at this collector current, IC, what kind of behavior would it have to the first order? Well, we will refine this equation, but to the first order, what do you expect it to be? Any thoughts? Well, what determines this current? What is the primary determinant of this current? This injected charge, right? Now, what determines how many of the electrons make it across this potential barrier? Is it any different from the diode? You're just lowering the potential barrier and they go, right? So whatever electronic current you got for the diode, so we had an exponential dependence. So it was e to the VBE over VT, where VT is KT over Q. At room temperature is 25.8 millivolts at 300 Kelvin. But it's KT over Q. And I actually like the KT over Q because it reminds you that this is a thermal device. Sometimes we summarize it, write it in shorthand as VT, the thermal voltage. Now, so times some IS, some proportionality constant, which has dependence on a whole bunch of other parameters. Among them is the area of this thing. And then it's basically the IC. So this is the collector current. So you can see that to first order, now you have the same behavior as the diode, except for the fact that now you have the current of a third terminal controlled by the voltage between the other two terminals. So it's really, to the first order, a voltage-controlled current source. BJT is. And that is very critical, because what it does, this exponential is pretty powerful. That's why I say it's a powerful device. It's an exponential dependence. So a small fluctuation here can lead to large fluctuations there, which is a good thing if you're trying to amplify something, or you're trying to have being able to switch something by having a small change in the input inducing a large change in the output, right? So that's the essence of the transistor. That's basically the essence of what the IS. And if you plot this quantity, if you plot this, I mean, it's an exponential, obviously. So this is VBE, and this is IC. And you will see that it's kind of a exponential, of course. If you plot an exponential on a linear plot, on a linear plot, what you will see is that you will see a region basically on any linear plot where this is pretty much close to 0. Now, of course, if you do it on a log-log plot, you will see something else. But so on a linear plot, it looks like that. So a lot of times, there's some what we call, to approximate as turn-on voltage. Sometimes we call it VBE on. Now, what VBE on really is a function of what IS is and what current levels you're dealing with. Because another way to see this, which is the inverse of this equation, is VBE is VT natural log of IC over IS. So it means that it has a weak dependence on the current, what the VBE is. So above a certain point, you will have a large amount of current for the scale that you're interested in. Now, if you change the scale, if you go from milliamps to microamps, then this transition will appear somewhere else. But still, it will look pretty steep and abrupt. And that's why there's this notion of VBE on. And we'll talk about this in more detail later on. But that's basically where it's coming from. There's nothing magical. It's just that exponential, when you look at it on a linear scale, for a certain range of currents, it will have a range of operation. And we'll discuss this in more details later. Any questions so far? Anything? So this appears to be good, right? I mean, are we good? Are we happy with this transistor? Is there something that we're missing? Is there any problems that you can identify? Did I sweep something under the carpet? Let's say we made the base thin. By the way, can we make this base arbitrarily thin, make it incredible? What happens if I try to make it thin, very thin? Okay, so that's a good point. So she said the depletion regions combine. What happens if depletion regions start hitting each other, start getting into each other? What happens? What happens to your energy band diagram? Well, so basically just drop, it starts becoming flatter and flatter, right? Then you don't have this behavior, then you lose your control, and you have reduced and eventually removed the isolation, the separation of the output port from the input port, from the controlled from the controlling, right? So you can't afford doing that, right? So now let's say, so that brings us to an interesting related question, which is, let's say I'm interested in making this base thinner because I'm going to make my transistor better. And I'm trying to avoid the problem that you correctly identified, which is that the depletion regions will hit into each other, right? Will go into each other. It's called punch through. That has a name, specific name. But what do we do? What do you think we can do?
Increase the positive doping concentration?
Yes, increase the doping concentration, right? He says, you mean here, right? Yeah. So if you increase the doping concentration, then most of the depletion region, if we follow this path, will become shrinks on this side, shrinks on that side. So the doping concentration. So what happens is that then you have a carrier. You will have a depletion region which is mostly on this side and that side. So that's a potential way of thinking about it. We'll see what the problem with that is in a second. But that's a very logical way of going about it. But what if I wanted to keep the the relative size of the not the doping. If I wanted to keep the relative size of the depletion region on either sides the same, I just want to shrink both of them by the same ratio. What would I need to do? You know what I'm asking, right? I'm saying that I want to shrink both sides of the depletion by the same factor. What would you do?
Other than just increasing doping
on all of them, increase the doping on all sides, right? So that's one way. And that's the basis for one of the things that happens in the scaling. If you want to make the transistor small, you increase all the doping content because you need to shrink all of these so you can bring these closer to each other. So these are not going to hit each other. So that's a good point, right? So that's one thing. But now, let's say if I do that, is there any problem with shrinking the base? So let's say I avoid. We design it such that the depletion regions will not hit each other for any of the practical voltages that we are going to be using. Are we good? Yes? Well, if we make it very thin, that's true. The electrons will tunnel over. But yes, and that's a good thing. We are not there yet. But if you make it very small, that can happen. We are not at that level yet, but it's a good anticipatory comment. All right. Any other thoughts? What would happen? Is there a more basic problem? This problem I'm talking about is very basic. Think about where these currents. There's some base current, right? Why is there base current? Where is this base current going, by the way? We'll talk about it in a second. But there will be some current in the base. Now, this current will be traveling in this direction, right? And if you make this thinner and thinner, you remember that slab that we drew on the first lecture? What happens to the resistance of that slab? If you make it thinner and thinner, you reduce its cross-section area. If I make this thin, the series resistance will go up. So you will have a series resistance here. It will keep increasing. And that can get in the way, because if you have a series resistance where there's current flowing, then you will have voltage drop. So some of your voltage drop is not really dropping across where it should be. It's dropping across hitting some resistor, which is not going to be used for controlling the device. So you lose some of the control, some of the sensitivity of the device. So that's another problem. And one way to deal with that is to reduce the resistivity, of course, as you scale it down, which happens by what? How do you reduce the resistivity or increase the conductivity? You remember the expression we had for conductivity? We derived it from microscopic level calculations. So what were the parameters in there? There was mu. There was Q, electronic charge. It's kind of hard to change that. There's the mobility, which is again not an easy parameter to change. I mean, there are parameters, but increasing it beyond a certain level is hard. And then there's n, the concentration of the charge carriers, right? In this case, it would be p because it's p-type. So how do you increase p? How do you increase the number of holes in the design for a piece of semiconductor? If I want to get more p's at room temperature, what do I do? What more holes per cubic centimeter or per cubic meter of it? More dopants, right? Which basically goes back to what we did already. So as you increase it, that's helpful. That goes back to, that's another reason you increase the doping concentration when you do scaling. Because as dimensions become smaller, you want to make the resistances the same or not increase as much. So anyway, but that's all good and nice. But so obviously we need to think about these issues. But let's say we have thought about this and we've designed this accordingly. So it has a correct right width. It's not too narrow, too wide. But now, is there something I'm missing? What is carrying the total current in this junction? Let's say this emitter current in that case would be carried by what? Electrons. Why electrons? What happens to the holes here? Aren't holes going backwards? As we lower the potential barrier, aren't holes being injected back because now we've shifted the potential barrier, so this thing has moved up. So now there's a whole bunch of new ones that can pass, right? So as we lower the potential barrier, not only electrons get injected from here into the base, there will be a bunch of holes injected from the base into the emitter. Is it a good thing or a bad thing? And why? So, good thing or a bad thing first? How many people say it's a bad thing? How many people say it's a good thing? All right. Why is it a bad thing? Yeah, go ahead.
Because you want those shear current carried by electrons, so then the collector current would be
right.
a greater ratio.
Right. Because if this whole current that's going back into the emitter is going nowhere right now, right? I mean, it's going to get recombined eventually here because there's no way to collect them, right? This is the bridge to nowhere, right? It's just like they're going to go and get recombined eventually. Unless you put another P here, which would kind of like be kind of a funny thing to, I mean, it would be an interesting thing to discuss, not funny, but that's a separate discussion. But if you want to keep it this way, you need to do something about this. There is an efficiency associated with this process. We call it emitter injection efficiency, which should make sense. The name should make sense. It's the efficiency of how many of what percentage of these carriers are useful carriers, right? Essentially, it's defined, shown with gamma. It's defined as IN of in the IN emitter over IN emitter plus IP emitter. That's the current in the emitter current, part of the emitter current that's carried by electrons divided by the total, which is the sum of the part that's carried by electrons and the part that's carried by the hole. Because if you remember this picture, there's some current carried by the electrons and some carried by the holes. So we want to make sure that this current, this blue one, is the component that's useful because that's the one we are absorbing afterwards. We're collecting. This part is not useful, the red part. It's getting recombined. So how can we, so what do we want this to be? Ideally, what do we want this gamma to be? Emitter injection efficiency. Emitter injection efficiency. What do you want it to be, ideally? Exactly, like most efficiencies, right? If you talk about an efficiency, you want it to be 100%. Some people aim for 110% of effort. But anyway, I don't know how they do it. Anyhow, so this is what we are trying to maximize. How do we do that? Propose solutions. And there are more than one solution.
One is few holes as possible in the p-type section.
So that's a good suggestion. He says, look, you want to start with fewer holes on this side to begin with. If you have fewer holes, so they have equal probability of going both ways, right? The Boltzmann distribution tells you what the probability is. But this probability is multiplied by the initial number, right? If the probability of crossing is, let's say, I don't know, 10%, if you start with 1,000 people, you will get 100 people that cross. If you start with 1,000,000 people, you will get 100,000 people that cross, right? So it's not just the probability of crossing, but it's also the number that is multiplied by. So it says, okay, control the number that's multiplied by. So in other words, have a lot more electrons here than you have holes here. Well, how do you do that? How can you make this device such that you have more electrons here than you have holes here? The density. Yeah. You suggested it, so why don't you? Well,
Heavily doping the emitter.
Heavily doping the emitter, right? So increase the doping concentration of emitter with respect to what?
The base.
The base. So we actually, we dope the heck out of it. Sometimes we show it as N plus. Sometimes we show it as like N plus plus something. But anyway, and meaning that you have a high concentration. You basically are looking at 10 to the 18, 10 to the 19, 10 to the 20 per cubic centimeter of dopants. And to the point that actually at some point it becomes degenerate. You have so many of them, yet you don't get more because of the interactions among them, and then you get ionized and all those things. So but you want to have a lot more. And if you make this ratio, for example, the ratio of doping concentration here to doping concentration here. So let's say this is 10 to the 18 and this is 10 to the 16. Then if you have equal probability of going in both directions, what can you roughly say your emitter injection efficiency is? Roughly. Well, yes, one is a good approximation. Maybe a little bit less. So I said 10 to the 18 versus 10 to the 16.
100 over 101.
Yes, which is 99%, roughly, right? Correct. Ballpark, right? 99% efficiency. So if I make this 10 to 1, it would be like about 90% efficiency. If I make it 1,000 to 1, it would be like 99.9% efficiency for emitter injection efficiency. But it is what it is, right? So that's one way to do it, and that's a traditional, classical way of doing it. Can somebody suggest a second way of improving? This is, by the way, done in almost all transistors. Can you suggest another way? By the way, is there a problem with doing this, first of all? There's a little bit of a problem, right? Because it means that your base needs to have a lower doping concentration, which was in conflict with a couple of things. One was this resistance. Two, but we can say, okay, fine, but it doesn't matter. I raise the doping concentration of both of them at the same time until I get the right resistance. Okay, fine. Two is this depletion region, because now the depletion region, if I have that kind of concentration, the depletion region will be mostly where? On the base side. Which, yep, it will happen. It does happen. And you live with it. So, can you suggest another solution? Can you think of another solution? What are the things that are controlling this current? We said there were two different things I mentioned, right? One is the probability of crossing. The other one is the density of charge carriers you start with, right? So we played with the density of charge carriers you start with. That was the first solution. And it's used in almost all, I shouldn't even say in almost all, in all bipolar junction transistors. That technique, the doping concentration of emitter is higher than doping concentration of base in all bipolar transistors that I know of. Yes?
If you lower the doping on the inside to get the depletion just almost touch, you get rid of most of the holes.
So the suggestion is interesting. So he says, if you lower the doping concentration on this side, then you can get these to touch, and then you will get rid of it, which is okay for the problem we are trying to solve, but it actually introduces a bigger problem, which is the lowering of this potential barrier, and you lose control. So it's a problem to a, I guess, first order problem, which is causing a zeroth order problem. But no, it's good thinking. I like the thing. I mean, so let's think. Let's continue. I mean, but yes.
You can cool the base so the holes don't have enough energy to cross.
So you want it such that you want to make it uphill for the holes. That's what you're trying to do, right? You're trying to make it uphill. But it's already uphill for the holes, right? But it's a good thing. So it is uphill for the holes. And it's uphill for the electrons. It's uphill for both of them. That's why you get the hot ones, right? Same thing is true for people, right? So it's a filter. But here's the thing. But actually, you're on the right track in a way. So the question is that I'm trying to reduce this number of holes, right? We played with the densities to begin with, but now I want to play with the probability. Is there a way to lower this probability? Yes?
You could change the semiconductor material used in the middle to make the electrons and holes see different potential.
That's a very good suggestion. So the suggestion is to change the semiconductor material in the middle. So use a slightly different semiconductor material in the base. If you could make that, then you can, and a slightly different semiconductor material will have a different band gap. And if it has a different band gap, you can make it so that it will be, let me use a color I haven't used, instead of where it was, now if it has narrower band gap, let's say here. So instead of this, you will get that. So this whole thing gets shifted up, which means that you have a larger potential barrier in one direction for the holes than you have it for the electrons. And this is the basic of what we call hetero-junction bipolar transistors, or HBTs, that are used extensively for very high frequency applications, particularly. So for example, silicon germanium transistors are like this. You have silicon, but then you have a silicon and germanium alloy in the base. And germanium having smaller band gap, the alloy will have a band gap that's determined by the ratio of the alloy. It will have a smaller band gap. And what happens is that you will get fewer holes. Now, what's the advantage of that? The advantage is that now you can live with the smaller ratios of the N to P. And you can have higher concentration of doping in the base. And as a result, your resistance is not going to be as large, your series resistance. Right? And the other interesting thing about it is that when you do this asymmetrical band gap engineering, they call it even band gap engineering, right? I mean, you can adjust it in different ways, and they become more sophisticated with that. But regardless, what is happening is that you can actually control that, and by controlling this, you can have a different set of parameters for this device. So this is called HBTs, heterojunction, as opposed to homojunction, which is basically made all of the semiconductors, the same semiconductor. You have a heterojunction, which are made out of different junctions, and you have basically something like that, and it's very common. The other combination is that they make it gallium arsenide, aluminum arsenide, gallium indium arsenide, or indium phosphide transistors. They actually can engineer the composition of these things. And in one of your homework problems, I think in problem set 2, you will actually analyze a regular bipolar junction transistor, and then you would change its base to silicon germanium, and you redo it. So all of things you will calculate quantitatively, and you'll see what happens. Anyway, any questions on this so far? No. All right. So so we can see we lose some of our electrons due to this back injection. You have some emitter injection efficiency loss because some of these electrons, some of these holes that are back injected. So these holes that are back injected are lost because they are going to be recombining here. Is that the only mechanism for losing some of our current? Would all the electrons that end from this side will end up back in the other side? So what happens to some of them along the way? They recombine, right? They are in a p-type region. There's a lot of holes there. So there's a chance for recombination. So you lose some of them through recombination. So there's another loss mechanism expressed as alpha base, which is basically called base transport factor, alpha T actually. So base transport factor, which is the ratio of the electrons that make it to the collector to the ratios of the electrons that are injected from the emitter. Right? So there's a second efficiency, if you will. How many of them make it across this no man's land in the middle, right? Just go across and without getting recombined. So you have this, and you have these two mechanisms, and there's a third one in the collector side, but since the collector is typically reverse biased, that's a small one, so it doesn't matter to worry about. We don't worry about it. Some textbooks put it in there, and then they say, and eventually they kind of, when they cut to the numbers, they say, oh yeah, this is almost 1, so throw it away. So let's not worry about that. If you were doing hardcore device physics, we would worry about it, but not here. But anyway, so there's this alpha, we call it alpha 0 or alpha DC. Alpha 0 also sometimes shown in alpha DC. Let's see, which is basically the product of these two, which basically is the ratio of the electrons that make it to the collector to the total current that's injected, or the collector current to the emitter current. Because the collectors that make it to the electrons that make it to the collector constitute this current, and the electrons that are coming out of emitter constitute this current. The current that you have to basically put in here. Well, you're really taking out of it because it's negative charge. So this current is IE, and that current is IC. And what you have here is that essentially IE over IC is going to be alpha 0. I'm sorry, IC over IE. Because this current is smaller than that current. Right? And where's that current going? You have KCL for this device, right? For this thing, it's a 3-terminal device. If it's a circuit, then this third current has to be the base current, right? So that's the current going through the base. So there's another way to see this, which is this picture. I'm going to overlay it on this with a different color. Hopefully it wouldn't make it too busy. So in a properly designed transistor, the vast majority of the current is carried by these electrons, right? Going across. So there's a big flow of electrons. Now, some of them are, this charge, what happens to this? So you have some of these electrons that are absorbed in the emitter. Well, let's just make this a little bit. So there's a fraction of them that's lost in the emitter. So and where does it go? It's balanced by the hole currents, right? So there's some holes that are coming in, and then there's recombination happening. So this is recombination in the base. And then you have also some of these holes that are back injected into the collector, right? Into the emitter, sorry. And what happens to them? Yeah, they would recombine with an electron there. So that would be contributing some of the current that needs to come in and balance that. So your total IE coming in has going to have two components. So this is the external current. So if you have an external current coming in, there would be this segment that's going there to make up for that, and this big chunk that's that ends up in the collector. So there's some loss here and some loss there. This is accounted for by gamma. This is accounted for by alpha t. Right? Make sense? Any questions? No? All right. So we can take these, and based on the alpha t, we can actually, so then alpha, and the other thing that we know is that basically the beta of the transistor, we define another parameter, which is basically the ratio of the base current to the collector current. And that's pretty straightforward to calculate. I'm just running out of space a little bit here. So let's try to open up some space here. And think about it. So we know that IC plus IB is IE by KCL, right? This is IC, this is IB, and this is IE. These two are going in, this is coming out. Net current, because of course, think about it. You're talking about electron movement, so the actual current direction is going to be the opposite of the movement of the electron. And then the other thing that we know is that we have IC over IE defined as alpha. Therefore, you can also say that IC, or IE, rather, is IC over alpha. And if you plug it into this guy, so you get IC times 1 over alpha minus 1 is equal to IB. Or in other words, you can see IC is 1 minus alpha over alpha IB equals IB. Or similarly, IC is alpha over 1 minus alpha IB. Now, we call this quantity beta, beta 0. So this is alpha 0 for DC. And this is a famous parameter for bipolar transistors. It's called beta. So IC is beta IB. So the collector current is beta times IB. Now, you remember, if it is alpha, we want it to be close to 1. This is a high efficient, if in a properly designed transistor. Let's say if alpha was 0.99, 99%, what would your beta roughly be? About 100, correct? So that's the parameter beta. But then the other thing that you see is that this is quite sensitive to alpha. So if alpha changes a little bit, beta changes a lot when alpha is close to 1, which is where you want it to be if you're properly designing. And that's why beta of a transistor is a pretty sensitive parameter. It has a very broad range, and you breathe on it, you look at it funny, it will change. Right? So it's not a good design parameter. You don't want your design to depend on beta when we get to design. Because if the design depends on beta, it means that the slightest change in the temperature or parameters or from one transistor to the next one will result in large changes in your design, which is not what you want in a robust design. In a robust design, you want something that is independent of these parameters to the extent that's possible. Okay, any questions on this? Nope? All right, so let's go off the record.